Okay, first make sure my mic is working. Okay. I'm going to talk about the exam 3, okay? And first of all, the problem is already posted. And here's the problem. Basically, step by step, to investigate the extreme value. And let me show you the response surface you're going to encounter. Okay, this is the response surface you're going to encounter. And I give you two different ways to look at this response surface. One is this view. Okay, and you look at the value from -5 to 10, -5 to 10, and I show you the max is about 244, probably just 2n. You guys see that? And then one minimum value is here. Okay, and this problem I used to call it the toilet seat. Okay, but I'll explain everything, okay? And your job, of course, to find the 2 max and 1 min. Or you can use the other chart to do it. Or you can mix the two. And this one is upside down. So max become min, min become max. You guys follow me? Now look at the variable, you know, except I just add a value to flip it upside down. Okay, now your job, of course, you know, you probably need to investigate this several times in order to. You just use this one to explain it. Okay, of course, the first thing is you need to find a starting point. What would be a good starting point to find the peak? You probably will say that. Well, let me start from somewhere closer to the peak, right? Right, from one end or from I'm sorry, it should be the peak here or the peak. So, how many of you will say that you want to start from the red zone, somewhere right around here?
So you're talking about using a good starting point to find.
Yeah, one good starting point for 3 things. You need to find the max and the min. So start from the middle point, good or bad?
Good for the min.
It's good for the min, but there's a very, very high possibility you're going to go find this local peak. Would you agree?
Yeah.
Oh, by the way, okay, you know, I just want you guys, there's no perfect answer for this. Even I give you the response surface. You know that in the real world, you're not supposed to know the global view, how it looks like, right? I don't care what, you know, banking, whatever industry you work for. You're looking for some good design or avoid bad design. But if you start from here, what you need to do in order to get to the other 2 points? One way to do it is what? After you're reaching this peak, you stretch out, or stretch out a little more. Because once you stretch out, you will realize that it drop and drop, right? So this is a good peak point. But the other way you can start is start from somewhere around this green area. But if you start from the green area, you'll come down easily, go up easily. But what is the problem is the other side. How can you find the other side? Right? So here comes another way to do this. What if you start from somewhere up here? You glide through, you glide through, you glide through. You follow me? And which point is a good point? there's no perfect answer. Okay? Now, let me show you, this is the answer from a previous study. And actually she did more than it's not. Oh, this one. Okay, and she investigates some pilot first, but here's the way how she did it. Okay, and I'm going to show you. She tries several different things, but look at here, okay? She has a 9-point, center point. This look familiar? You know, she started from 1 point, and she checked the quadratics is not significant. Keep going. And iterations after iterations, once she reaching a good starting point, okay, once she reaching a good stretching point, she will add a stretching data point. And of course she investigates several different possibilities. I want to show you guys one thing. She's very smart doing this. She will copy a section of this. So remember we said that we're going to have the data like this, and well, what she did is once she say here's the stretch, here is the quarter, right? The 4 corner and the center point. She needs a stretching point. When she needs a stretching point, she rather than using well, let me put it out. Or you can save it differently. Is what I'm trying to say here is we know that here are, oh, by the way, he is not doing what you said. Remember, originally you said, oh, what if we just have 5 by 5 to define the box? She only used 3 by 3 to define the box. Okay, and what I'm trying to say here is that once you're reaching the starting point, you need to find a quarter. Okay, and what she did here is using, well, let me see if I can make it. Can you guys see? I'm going to just do one side so you can see it. Okay. People, first, everybody know how to make the 4 corner point and the center point, right? But now we said that we need to stretch out 1.414, a quarter. So one thing you can do is, okay, if this is a quarter, see here, from A to, okay, so if here 0.5, okay, see here, 0 is at 9, right? Right? And then 0.5 is 8.5, it's 1. So what will be negative 1.414 will be A or a little more than A. You guys follow me? It will be just a little bit more than A. Okay? So one thing you can do is, well, I'm trying to do it the same way, is you copy paste this entire page, okay? And she did it more than once. Look at here. Okay? Here is one example. 0.5.
You
No.
can't see that cell.
Yeah, well, that's my problem. Okay, I'll make one up here then. Okay, so you know that this should be what? This should be 9 minus square root of 2. Okay, first, here is, let me do the other side first then. 9, and I know 9.5 is 1, right? You guys follow me? 0 is 9, 1 is 0.5, right? So here should be what? 0.5 times square root of 2 minus 1. Huh? Huh? I got it wrong? No. Let me try it one more time. This should be this times square root of 2. That will be more than 1. But I don't want to be more than 1. I just want to be a little bit, the extra of the 1. That's what I'm trying to show. Okay. This is your square root of 2. You guys follow what I did? That is your stretching point. So when you sample, you need your sample stretching point. Here is your first stretching point. You follow me? Everybody see what I did? I don't want you end up coming back and say that I don't know how to come up with that quarter point. And then here is another one. Okay? On this side, the same things, plus SQRT 2 minus 1. Let me see. Double check. Okay. This guy minus this guy should be more than a little more than, less than 0.5. Yeah, I got it. Okay? And once you got your 9 point done, actually what I will do is like what she did is she copy paste this to another sheet and just call that sheet is to find the stretching point. Originally, I only used this to show you how to find the square and the center point. Agree? Right? You find a full corner and then sample 5 times. Just use Control S to find the center point. But once you have that done, you now need, you don't need to find a stretching point until you reach a local optimum or a local minimum. So when you reach in the local optimum, local minimum, you need to find a record and say that, I need some stretching point. And here is the 4 corner of the stretching point. You guys follow me? Yeah. Now let's go back to the problems. Okay? Use response surface A or B or combination of the two, find the extreme point. Okay? Your job is to find the extreme point. Okay? Identify a guess which problem is the hardest problem in this whole thing. Problem number 2. Okay? You will try several different versions. So in reality, you could end up with several iterations, different route until you say that, oh, now I find my sweet spot. Okay? And define your 4 corner and 5 center point, or just collect. Okay? And run RSREG, find the directions of improvement. Okay? Investigate if you're reaching a stationary point. Okay? And then find a new location for the progressions. Here is one thing possible, okay? Is once you find the peak, okay? And then you just said that I don't think this is the right peak. What can you do? One thing you can do is what? Build a huge square cube. Can you build a very, very large cube? Because when you build a very, very large cube, you will see these things drop and increase again. You guys agree with me? If you see here, if you don't stretch out far enough, you won't see there's another peak to climb. So you need to stretch out far enough to say that, oh, I find another peak, another way to climb. Then, in other words, is there any rule? I said that you can only define one square, or you can have more than one step size. What do I mean by that? Is you can use this, one square size to find this peak and this valley. Okay? Now, after I find this peak or this valley, why I want to stretch out as far as I can? Because if I stretch out, no matter how far I stretch out, it's smaller, never go up, then I know this is a global maximum. Agree? But if I go stretch out, and then I see that this thing's getting up again, then there is a possibility something else is going on this side or on this side. Okay? So, in my opinion is that you can start this way or this way. Or you can start by just say that I'm using the center to go up and down. But then after I do that, I just need to stretch out a little more to find a maximum. Okay? That's the first things I would like to talk about. Another thing is that probably it's not important in this exam problem is what if, okay? This has got nothing to do with the exam now. In other words, this one is not in the exam. But anybody can tell me if I have no idea what kind of response surface I'm really involved. In other words, is that I've never been in this business before. This is the first time I've encountered this. And then there, of course, real world situation, there's no picture for you to look at. And now I would like to find some good starting point to start my investigation. Anybody can tell me what will be your approach to do this problem? You guys follow my questions? You got hired by some big company. The big company say, hey, you're young and you're innocent. You never done in our business before, we would like you to try a new product. And here's some funding, some time for you to investigate, for the Navy shipyard or whatever, okay? But if you said, well, is there any pilot study, anything done before? I said, nope, we don't have anything. We want you to start from scratch. But it's a response surface problem, okay? How are you guys gonna investigate something in that nature? Anybody? How likely you think you could encounter a problem like that? COVID-19, we hire a few people who would like to see how far can you think independently. Anybody can suggest a way to do it?
Start in the middle.
Huh?
Start in the middle.
Start what?
In the middle of the spreadsheet.
I'll start from a new spreadsheet. Yeah, I'm doing that.
No, in the middle of the data. Like in the center.
Oh, but let's just say that I don't know where's the center. Okay? Here's the approach I will use. Okay? Let me just say that I started with this huge, I don't know, thousands of points of experiment. Okay? I'm only do this. Okay? I'm going to just randomize, random sample this. Okay? So now this bunch of random number, right? And once I have the random number, okay? And this, you guys later on, for some of you involved in machine learning, you can see that. Oh, shoot. Pay special. Let me log the value. Pay special value. Okay, once you log the value, okay, pay special. You only do this. You'll say that, okay, rank. Okay? This value among the total value. Okay, that's 299. And then I'll do it again. Okay, now I have basically, I don't know how many number, right? But this time, I'm going to just say that once I have all the random cases built, okay, pay special, okay, value. All I care is what's the total number here, max. Okay, I can use me. Okay. If this value, can you see it? Yeah? If this value is less than 30, then I will say 1. Otherwise, I'll say 0. So if I do this, people, how many value I will have in this chart? 30, right? So now what I will do is using, Victoria, are you with me?
Was there any reason? And why did you pick 30?
But I'm just saying your budget only allow you to random sample 30 times.
Okay.
Okay? And then, so once you have that done, then, okay. This will equal to, okay, every observation times your sample value. So now people look at this. How many value are you going to have?
30.
Only 30, right? Everybody with me? And once you have this 30 value, okay, what will you do? You bubble sort them. You bubble sort those 30 value, and if you're looking for max, I'll use, say, the top 5 or top 3 as my starting point. So think about it this way, okay? If I started by using the max, okay, you can tell, I'll start somewhere around 400 or, well, I don't know, on this side. Okay? And I'll see some value. So then if I'm looking for minimum, I will use the lowest 3 value as my starting point. You guys see what I'm doing? Your boss said that, hey, find a starting point. And the problem I give you is that you kind of know where's a good spot to start. Even though there are death traps, you need to do something about it. But in the real world, it's not going to be like my exam. What if you encounter a situation, no idea where to start, right? So what will you do is, well, you need to say that, well, I need to have some pilot study. And the boss said, well, do some random survey, do some random check. And what will be your next questions? How much money, how much time? And the boss said that, well, I'll give you 30. And then you're going to do this 30. Now, would you have all your 30 in this cage? Because you gamble too big, right? And of course, there are people, and then of course, in the case I give you right now is how you random sample. You use the entire space to do random sample to find that 30 points, right? There's another way you can do it, okay? So far so good? There's another way people will do it is this, okay? They'll highlight a few area and said that, oh, well, let me do it this way. They'll highlight a few area and said that don't sample around this area. Don't sample around certain area because we know there's nothing good there, okay? And if you can kind of like block certain area, and so if you have a sample in that area, you give up. Said, oh, I'm in the pink zone, okay? I will find another sample point. So your sample points will focus on certain area or avoid certain area. You guys with me? This approach, okay, copy it, okay, in response surface or in data mining, there's a name for it, okay? The name is called Taboo Search. Anybody heard that before? Nobody heard Taboo Search before? Taboo Search is a meta-heuristic search method, employing local search method used in mathematical optimization. What is taboo? Taboo is a forbidden zone, right? Right? So you basically, when you sample, you basically try to say that what area I need to avoid, okay? There is another thing you can do, actually relate to this starting point, is you can highlight certain area and say that I think this area is a sweet spot, got more chance than other area. And then you can start weighting them and say that, okay, I'm going to sample certain area. Here, what I'm trying to say is this. If I'm doing it this way, okay? If I'm doing it this way, people, is it possible that I can say that I have 30 sample? I will circle zone 1, zone 2, zone 3. Okay? Those 3 zones, I will allow me to have a sample, a sample, a sample. So I will use up how many? 24. And then I'll circle certain area and say that I would like to sample here. Oh, I'll sample here and here. Each got, I have 6 samples left. So I'll say that this area and the other area, I have 3 samples, 3 samples. So here find 3 samples, here find 8. That way, you basically build what? Some intelligence in investigating where is the good spot. Okay? This usually requires you to do some literature review or talk to previous supervisor. Okay? We have people work in the airline industry. Say, I'm working for airlines, okay? And they send me to a new station, say Singapore or Qatar, whatever I never been to before, okay? And then when I get there, would I immediately start doing my inventory, investigate my optimum strategy of doing stuff? Or the first thing you do is what? Talk to people who are already there, right? Talk to the crew chief. Hey, how's our mechanics here? How's our record here? How's our OSHA logs on injury or workers' compensation? Any major event and stuff like that. Why you want to talk to people like that? Why you want to talk to some senior already there? They can tell you where are the based on their gut feeling, where are the good spot to investigate, to find good answer, and where are the places they'll consider, don't even bother. There's no good answer there. Stay away from there. You agree with me? Yeah. So this is the things that about a starting point. Okay, show hands. Everybody know how to find the 4 corner, find the center point, how to find the stretching points now. Everybody? Okay? So, no problem?
I'm still a little confused on just like, when you start,
Mm-hmm.
because you showed us that like the scattered with like the 30 points,
Mm-hmm.
but I'm still confused on, I guess, like how you choose where to go and what you're looking for in that start. Like, how do you know you're done finding the starting point?
Mm-hmm.
Look at the iterations. I don't understand that part, I guess.
Okay. Technically, you may have some gut feeling is going that way. There are some good answers. So let's just say looking for max, right? Okay? Now, if I started from this side, completely start from this side, okay? Would I find a good maximum point? Yeah, it's this one, right? But how likely, and probably I can find this one if I run another iterations, right? But how likely I will find this point? Less likely, right? So remember the exam problem I give you is find a sweet spot, a good point to investigate all the extreme points. So if you're, well, no, time out for 1 second. If I give you, or you have million trials, okay, sooner or later you will find everything. Would you agree? Go up, go down, sooner or later you'll find something, right? So our job, of course, is find a sweet spot so I can have minimum number of iterations to find 1, 2, 3. Agree? Agree? So based on this, intuitively, you said that maybe I'll start from here. This is good, right? But why this problem is tricky is because I already show you there is a potential spot for you to get trapped, because you will find this point and then you'll say, oh, I found a max. But that max, since you already know, it's not, this is not a Shangri-La. This is the pseudo Shangri-La. Okay? Okay. Then two things you can do, right? One is mechanically. You can say, oh, let me build a stretching point out far enough to know that, man, this thing will drop again and come back up again. So obviously this point could be a local max. Agree? So if you stretch out this side and then you reclimb, stretch out this side, you reclimb. Okay? There is another possibility. Okay? That is something I actually, I try to, okay, fine. Advanced topics. Do you think it's possible sometimes, okay, I know what example I can give you guys. Sometimes you choose school to study, choose jobs, choose spouses, okay? And then there are rich, famous, something will be very, very good in every possible scoring system. Do you always use that as your guiding light? Or sometimes you will say that, no, he's the richest, but I'm not going for the richest. He's the most famous, I'm not going to go for the most famous. I'm going somewhere a little below. Is that possible? Why you do that? You follow me? It's kind of like, oh, I'm supposed to pick the most, most beautiful, most handsome, most whatever. But I actually say, no, I'm not going to go for that. Because you're still looking for something extreme. But if you go for the max too early, you could end up stop right here and not finding anything new. So you go kind of like, let me at the beginning, not choosing something this big, is you're trying to see if I use a percentage, I can curve and go up this way, curve and go up this way. You follow me now? Yeah? Okay. So like I said, this part I don't, for the review so far I'm just want to make sure everybody can find a starting point, find the four corner, and do the iterations, and then doing the stretching point and said if it's okay. We all have the same toolbox. That's all I want to guarantee. But what is the best strategy to do this? I don't want to limit your thinking, because that's your imagination or your I want to see if you can think for different approaches. Okay? Make sense? Okay. Let's go back to the lecture now. Okay. Before I start the lecture notes, final pieces, everybody, no problem. You can do it now, right? Okay. The mechanics is clear, right? Okay. What happened? Okay. And you know how to find the directions? Okay. The part that find the eigenvalue and eigenvector, okay, you will always, the SAS output will give you two eigenvalue. Okay? If both eigenvalue, when you have the stretching point, are positive, if both eigenvalue are positive, then you have a minimum, because either going this in W1 direction or in W2 directions, your value is going up. So it's in this point will be minimum. If both eigenvalue are negative, then this is maximum. One eigenvalue is positive, one eigenvalue is negative. You know you're reaching a saddle point. Okay? Next. What does eigenvalue really means? Anybody know what eigenvalue really means? You had linear algebra before, right? So what does eigenvalue really means?
Character value?
Huh?
The character, like how it behaves.
Yeah, and what is the characteristic value really means? Keep going.
How it behaves.
And how to behave. Here's the things, okay? To calculate the eigenvalue, your equation. Let me just use. Okay. We always calculate the eigenvalue by using summation, the matrix. You know, in our case, is the B matrix minus lambda I equal to 0, right? Right? In your linear algebra, you remember, is this minus lambda I is what? The unit in this case is 1, 1, 0, 0, right? So what does this matrix minus lambda I equal to 0 really mean? Means that the area defined by your A matrix and the area of your lambda times 1, 0, 1, 0, 1 are the same. So look at the problem we have here is that I have a surface, right? and this is going up. So to define this quadratic area using those those B terms, and using my eigenvalue times eigenvector, we are representing the same baseball cap, or same mountain, or same saddle point. But how many, here, if I have a baseball cap here, I hold it upside down, or I hold it this way, okay? How many coordinate systems I can have? Even I can center it, say this is my peak. How many different ways I can how many coordinate system I can have? Infinite number, right? But which one is the best one to have? Victoria, that's your term. The characteristics. Here are the long axes, here are the short axes. So now I'm saying that I can use the characteristics W1 and W2 eigenvector to represent whatever your x1, x2. So when I said that I'm trying to find my eigenvalue equal to 0, I'm really trying to manually figure out where is that point, okay? So do it once. We find our quadratic term. Since it's a quadratic term, here is the x1 square, here's x2 square, and here is x1 times x2, and they should be equal. And you should have exactly the same things. And here is my linear term. So this is the parameter beta 1, beta 2. Here's beta 1, 1, beta 2, 2. Okay? And even without looking at my eigenvalue and eigenvector, people, look at this. A square, x1 square, the parameter is negative. x2 square, the parameter is negative 1.001, is negative. Both x1 square and x2 square are negative, and this is a stationary point. What do you think? This stationary point, without calculating eigen, is peak or max or mean? Just by looking at this. x1 square, the parameter is negative. x2 square is negative. If it's negative, means that no matter going to the left, going to the right, no matter which direction I'm increasing or decreasing x1, my value will be increasing or decreasing. Will be decreasing, right? Except at a stationary point. Same thing, x2 is the same things. So you can, just by looking at this, I will say that unless there's a saddle point, just by looking at my gut feeling, I know that x11 or x1 square is negative. So this must be a peak. Here must be another peak. So peak. So probably is a peak. And of course, if you have one peak, one negative, then that's a different story. Okay? Then using this, okay, you can, using Excel to calculate it and figure out where is your stationary point. And once, okay, step number 1, you find your B parameter and your capital B, you should be able to use Excel, SAS will tell you where is your stationary point, but you can use Excel to calculate the stationary points. Agree? Can you calculate B inverse? Can you calculate B inverse times B divided by half times negative 1? This can be done in Excel too, right? So you can double check. Make sure you have your stationary point. And then, of course, you can convert your stationary points back to your natural variable to figure out where is your natural variable. So natural variable is 5 times x1 and x2 minus plus 85. So you get your natural data point here. And Again, SAS will give you the answer directly. Finally, here is the how to calculate an eigenvalue and eigenvector. Everybody, can you see that capital B is x11 square, x12 parameter, and beta 11, beta 12, and beta 22. That is your capital B matrix. And so capital B matrix representing what? The baseball cap, right? And or a landscape. And minus lambda times I. If this thing's equal to 0, what does it mean? The volume, I don't care you're talking about a volume of a baseball cap upside down, minus the characteristics. Okay? The two volume exactly the same. That means that you use whatever your B, beta 1, beta 2 to talk about the volume. I'm using characteristics to talk about that volume. That should be the same volume. So by doing this, you'll have your quadratic term identified, and then you can solve your quadratic term. If you want to use an Excel solver, that's fine. You want to just look at SAS to compare your answer, is fine. But here, I would tell you that you only need to find using the quadratic term how many times in our problems. One, two, unlucky, 3, and 4. Okay? So you only need to solve the quadratic terms 4 times. Okay? And once you do that, you can find your eigenvector and your eigenvalue. Oh, time out for 1 second. When we solve the eigenvalue, okay, eigenvalue 1 is negative. Eigenvalue 2 is negative. What does that mean? According to the rule, eigenvalue is going down, down. Eigenvalue 2 is going down, down. So find my stationary point is a peak. Okay? Everybody with me? Finally, okay, you can just recover this by saying, oh, I can express my eigenvector and my original value the same way. Okay? For your exam, I would like you to, report every SAS steps. Okay? Show this. You don't need to give me the SAS code because it's exactly the same things. But show me the let me open one. Yeah. The SAS step will show you, what is my eta, what's my x for your initial and progression point. And then find your parameter. And you should have the plot to show that you're going up or going down. Okay? And move to the next point. Next, let me you should give me a final data point. And when you're reaching the final, Okay? You should show the data structure like that. And you should also tell me your quadratic and your interaction terms are significant, or either one of them are significant. And finally, report your eigenvalue and eigenvector. And here, this is the example. You guys are not in, but I just want to show it to you. This one, see the eigenvalue? One positive, one negative. What does it mean? Which kind of stationary points I'm in?
It's a saddle point.
It's a saddle point. Okay? If you're in the peak, you should have both eigenvalue negative. Okay? And then you also will have your eigenvector to show you how to convert the eigenvector into the answer. Okay, SAS automatically done all the what you call that things, residual legal document. Okay, you just keep it there. We don't need to do residual analysis this time. Okay. But you know that I mentioned this in real world situation. I don't care you're doing factorial design, blocking design, or the simple single treatment experiment. When you're done, you will have residual left. You need to have a document legally to show that your residual are independent, identical, equal space, and no autocorrelation, Durbin-Watson, that kind of a document. Here, you just let SAS do it for you. Okay? So when you finish your exam, please do this. Show what is your first iteration, what is your second iteration, a simple thing to show that your quadratics is not significant, so you keep moving, until you're reaching a stationary point. And when you're reaching a stationary point, add the stretching point, sample, run the SAS again for the eigenvalue and eigenvector. Okay? So is that part clear to everybody? What should be turned in your exam? Okay? Clear? Yeah. I think I will also probably load another set of demo videotape on top of this for people who just said that I want to just follow, even as wrong steps. I just want to follow the wrong step, step by step. But I personally think that if you just want to plug and play this whole things, this is really not the reason we have this exam or this exercise. The reason we have this exercise is to force you to think about it. What if I don't know anything? What if I only know a little bit of something? How can I use what I know to investigate what I don't know? Okay? Okay. If you don't have any questions, then I'm going to get into new topics now. Okay. The topics I'm going to get into are three things. One is called, they are actually related to random effect and fixed effect. Okay? And the example Well, let me show you the fun stuff first. Maybe that will trigger your interest. How many of you ever heard Taguchi Method? Yeah? And what's the Taguchi? Anybody know what's Taguchi Method?
Taguchi is robustness, correct?
Uh-huh. And what does it mean?
That's a great
And-
question. I'm sure you're going to tell us.
Huh?
I said that's a great question. I'm sure you're going to tell us the answer.
Okay. How many of you ever heard about the big three losing business in the 80s after two oil crises? This is related to Iraq too. Nobody? Okay. How many of you know Americans used to be very, very proud about their muscle car? Well, even today, if I can have I don't want to have Tesla, I want to have a Mustang. I want to have a V8. Okay? Because, just the sound is much better than no sound. Right? And so in the 50 and 60, U.S. dominated the world with the car manufacturing, was everything, right? And what make U.S. Car industry suffer? Oil crisis. After the second oil crisis, people start saying that long lines at the gas stations and no more gas. So you have a muscle guzzler V8, you're in big trouble, right? And so at the beginning, people make fun of Toyota and say that's just a toy car. It's nothing. But suddenly, because of oil crisis, having a V8 versus a 4-engine, suddenly it makes a lot of sense to have a small car. And then when they start playing with a small car, they realize something. Okay, well, there are two parts. And American, of course, they said that how can we give up the small car market? They want to do the small car too. Okay, but one problem immediately showed up is when car in trouble. When you have a V8, what's the beauty about, open the hood of a Trans Am or a Mustang, the old one? You can see everything. Your hands can reach everything. So you can, you want timing belt, I can touch timing belt. You want the convert, everything's, it's there. It's easy to reach because the car is big. Now suddenly you have a very, very compact car. Can you reach anything? You can't. So maintenance become issues. And of course, later on, people start talking about so-called modular design. I don't want to repair anything under the hood. I just pull one drawer out, pull one module out, put another module in to minimize the maintenance time. Okay? And military loves that because they can always have their F-16 standby. You don't put your vehicle, your airplane in a hangar for fix. But now suddenly they realize, how come the Japanese car is always running without any problems? Okay, it's a lot more reliable, a lot more consistent. So when they realized that, they found out that the Japanese follow a quality control or experimental design philosophy, okay? And then they said, oh, the guy behind this is Taguchi. But then they checked, hey, Taguchi, where do you get all this statistical experimental design skill from? Guess where he got his skill from? Another guy, his name is Deming. And guess where Demings used to be? In US. He tried to tell American company that they need to do experimental design, they need to follow quality control, a lot of stuff. But US kind of like, hey, we're having fun, everything's fine, why should I listen to you? So Deming got no audience. So he started preaching his stuff in Japan. The Japanese, on the other hand, they have limited resources, limited everything. They said that, oh, this is something we should learn, to be lean, to be Six Sigma, whatever. So they start doing it. Okay? And later on, guess what Taguchi did? And including his son. They wrote back to the big three in US, says that we got a lot of benefit from Deming. We would like to share this with you, see if you're interested. So, Ford started a American Quality Institute around 80. Ford Taurus is the first semi-compact sedan that followed all of those principles. Okay? And then when they follow those principles, they start building their quality control system, and combine the quality control system, TQM, Taguchi's method. There's another things used in the processing. All system engineers should know. How many of you ever heard JIT? Huh? Just-in-time inventory system. And what is just-in-time inventory system is about? Is pull, not push. And why I'm talking about this is that the American manufacturing system in the old days is based on the abundanceness. We have tons of inventory. We have tons of resources. Why? We can afford it, right? People talk about how U.S. won the Second World War on two fronts, Pacific Front and Atlantic Front. And a lot of time people will say that, because we have, wonderful General MacArthur, Patton, great soldiers. No doubt about that. But do you think that the German weapons terrible, Germans general stupid? There's also another side of this, is American just got abundant resources. They can build the B-17 bomber, I think it's like one day, one push. They can build Liberty ship to counter the U-boat attack. I think it's like 1 week per boat. Just keep pushing it out, pushing it. You guys can check the statistics. But this is the thing is that, you can fight with me. Guess what? I just have plenty and plenty of resources. I can just keep building it. And you just cannot fight against that. But oil crisis make the world change dramatically, because the ship line, just like COVID-19, suddenly got truncated. You don't have enough inventory. So people start talking about we need to have good inventory, high quality inventory. And the other thing is that don't overstock. I need 5, I only stock 5. I need 10, I only stock 10. So I need to control the inflow of the material. I also need to control the quality. And the push and pull system really is the foundation of, some of you love to talk about Lean Six Sigma. The pushing system is, I don't care if you need it or not, I'm just keep pumping it. So sooner or later, you're jammed with tons of extra. But if you have a pulling system, you don't get one until you need one. So you're pulling it, you don't have the waste of inventory, you don't have the waste of your manpower, you don't have the waste of your space and everything. Okay? And so now I'm trying to give you the big picture is that Taguchi, okay, it's related to the entire quality control, but also related to how to introduce quality experimental design back to US. Okay? Now let me, I think I drew it last time. I just want to do it again. Is in the quality control, okay? Can I see it? No, I got the name right. It's the robustness. Okay, so I would like to Taguchi robust design. What does it really mean? Huh? No. The robust design is something like this. Okay? I can have the same input with this much of variation and this much of variations. Okay? And whenever I have the input variations, I will causing this much of output variations. That's bad news. What I want is I want to have a lot of variations of my input, but my input is robust. The variation is small. So first thing, put it down. Taguchi robust design, or the core, the most important concept about robustness based on Taguchi, is insensitive to the environmental challenge, insensitive to the variations of the situations. Okay? So, I have oil crisis, I have COVID-19, I have a lot of environmental uncertainty. And whenever I have the uncertainty, if I'm sensitive to that uncertainty, my output will have a lot of variation. But if I'm insensitive to the variations, I'll have very, very little variation. And in this case, if I'm looking for the max, okay, this is not only less variation, also has higher output performance than this one. So what will be a good design is I'm finding a max, and this max is what? No matter how I stretch, how I look around, max is still the max. You guys follow me? So put that down, okay, memorize this, because if you out for job interview, people will talk to you about all those factorial, whatever, F statistics, but they probably will say that, oh, you're a system engineer, do you know what is Taguchi? And you should say, Taguchi is about robust design from experimental design standpoint. And of course, the follow-up question is, what is robust? And you should say what? What is robust? Insensitive to the perturbations, to the disruptions. Okay? So what I would like to finish this semester is talk about the Taguchi, and then I will cover that with other variations of the material. We have, what, 3 or 4 more lectures left, right? Huh? Yeah, that's good. 3 will be good enough for me to finish it. Okay? And for exams 3, due on when is our final day? I think it's December 8th, right? Yeah, so December 8th is the day graduate student turning in your term projects and your exam 3, okay? One more, okay? I already said it more than once. You guys want to discuss? That's fine. But please, don't copy-paste other people's spreadsheet and turn them in. If you do it that way, you just really force me to turn you into the dean's office, and then you're going to face all kinds of troubles, okay? Try to do the investigation yourself, okay? Please don't copy paste other people's material. That's just, it's not right. Okay?